Hi, my name's Anish Agrawal, and this video is for Chemistry 102 Mentoring. I will be solving a titration calculation problem. In this problem, we are asked to find the pH of a solution formed when 45 milliliters of 0.1 molar sodium hydroxide is added to 50 milliliters of 0.1 molar acetic acid. It's important to note that a strong base, sodium hydroxide, is being added to a weak acid, which is acetic acid. For any titration problem, the equivalence point is where moles of acid equals moles of base present, regardless of the strength of the species. In this problem, we have equimolar solutions of different volumes. Since the base is 5 milliliters less than the acid, there are less moles of base than acid present in the reaction. We are therefore before the equivalence point, and since there is more acid, it's important to take quick note that we should expect the answer to be slightly acidic in pH. Using the given information, we can calculate the moles of each using the molarities in the volume. So we have 50 milliliters of 0.1 molar acetic acid which gives us 5 millimoles of acetic acid, and we have 45 milliliters of 0.1 molar sodium hydroxide, which result in 4.5 millimoles initially present of sodium hydroxide. Now we should write the reaction that occurs between the acid and the weak acid and the strong base. So we have acetic acid, which is aqueous, and sodium hydroxide, aqueous, resulting in the acetate ion, and water. Acetate is also aqueous and the water is liquid. So initially we start with 5 millimoles of acetic acid, 4.5 millimoles of sodium hydroxide, and none of the acetate ion. The 4.5 millimoles and the 5 millimoles of the sodium hydroxide and acetic acid will result in partial neutralization occurring. So the 4.5 millimoles will be consumed. And at the end, we'll have 0.5 millimoles of acetic acid remaining, none of sodium hydroxide, and 4.5 millimoles of acetate ion. So now we have weak acid and conjugate base left. Since these are left in the solution, the following reaction occurs. So to calculate the pH, the H plus the hydrogen concentration remaining must be calculated. Let's calculate the molarities of the acid and base remaining from the initial reaction. So first we must realize that the total volume isn't the combination of both volumes, so we have 95 milliliters, which is the total volume now. So the concentration of acetic acid remaining is the 0.5 millimole divided by the total volume, which results in 0.0053 molar, and for the acetate ion, we get 0.0474 molar. So rewriting the equation, we have 0.0053 molar acetic acid and 0.0474 molar of acetate ion. And since we don't know the concentration of hydrogen which we are trying to find to get the pH, we can mark it as X. Now we can set up the equilibrium constant expression. And plug in the values from above. And when we solve for X, or the hydrogen ion concentration, we get 2.01 times 10 to the negative 6 molar. We can convert this to pH by using the following equation. pH equals negative log base 10 of the hydrogen concentration. Plugging this in, we get a pH of 5.7, approximately 5.7. We could have also used the Henderson-Hasselbalch equation, which would have worked just as well here, which is pH equals pKa plus log of the concentration of the conjugate base over the concentration of the conjugate acid. This would have worked as well and given us the same answer of 5.7.